until now, all the differential equations that you've seen have been something like y prime equals the function in relation to x, or something like this equals the function in relation to x, and you've been able to solve them just using all of the theories of calculus and things that we've learned this far. But starting in section 8.4 in the book, when you look at differential equations with growth and decay, you start looking at equations that have two variables in them, like y prime equals 2x over y. And the way that you go about solving these is to get everything onto one side, so you do y prime equals 2x, and then you'd integrate both sides. So you do the integral of y prime dx in relation to the integral of 2x dx. And then you'd go about bringing the dx over to the other side, replacing it with dy, and then you'd integrate both sides. So in this lesson, we're going to be going out just about how you do this and what it really means in terms of why you'd be doing this. Alright, so the first thing you want to do when you're learning these is to look at the way the equations are usually written and the way the solution is usually written. So in a growth and decay model, it will be written usually as the derivative of y over the derivative of function t is equal to some constant k times y. So you look at the rate of change of y over the rate of change of t. So y is a function of t here. So t would be time, and y is the rate of change of time. And k is just some constant. So the rate of change, you could say, is proportional to y. So the reason that's important is because of the solution. So the solution is actually a theorem in the book, theorem 8.8, called the exponential growth and decay model. So it's written in this form. So you see some common things here, t, which is time, k, which is the constant, and then the rest of this. So the way you want to look at this for the important parts is that y is always going to be greater than 0 as a function of t, and that y prime is going to be equal to the value of constant k times y. And the reason that this is important is because k, in your final solution, if it is less than 0, then you're experiencing exponential decay, and if k is greater than 0, then you're experiencing exponential growth. And that's the entire reason you'd be putting it into this form. Alright, so now to go over this. This is always going to be the initial value of y, and then y and k are always going to be proportional to each other. K is just going to be some constant, t is time. And that's all you need to know about both the form of the equation and the form of the solution. So now let's move on to a practice problem. Now what you might notice about this problem is that there is a derivative of time, but there is no actual time variable here. And I thought this would be a good one to go over for that reason. So the first thing that you do would be to isolate the variables by themselves on either side. So I'm going to move the derivative of time over here by doing a process kind of like multiplication. It's not actually multiplying by the derivative of t, but it makes it easier to work with that way. So you'd be left with dy equals negative 1/2 y dt. Then you'd move this whole thing over to get negative 2 dy over y equals the derivative of t. The next thing that you do would be to integrate both sides of the equation. So you'd have the integral of negative 2 dy over y is equal to dt, or the integral of dt. So let's start with the hard part first, and we'll do the integral of dt, which the integral of this, well, technically it's 1 times dt, but this doesn't matter. So the integral of this would be just t, but never forget to add your constant at the end, so it would be t plus a constant, which we'll call constant 1. Okay, so that's going to leave you with the integral of negative 2 dy over y equal to our now integrated other side, which is going to be t plus some constant. So next we're going to integrate the other side, which happens to be a little bit more in depth. So to integrate negative 2 dy over y, you have to know something important, which I will get to in a second. So the first thing you'd want to do is to remove the constant. So you'll rewrite it as the integral of negative 2 times the integral of dy over y. Now, what I was talking about before is a pretty easy way to do this, which is the common integral. So you can rewrite this as negative 2 times the integral of 1 over y dy. And the reason you do that is because that is actually equal to the natural logarithm of y. So that is going to be equal to negative 2 ln, which is the natural logarithm of y. And then, of course, don't forget to add your constant back in. So this is going to be our constant 2. So after all that, you're just going to combine both sides together in one equation, which is just going to look like negative 2 natural log y. And then you can combine the constants here because it doesn't really matter what the actual number is in this case, so you can put it on either side. So I'm going to actually choose to put it on the other side here. So then you'd set this equal to our other one, which was t plus our constant. And now, like I said before, you don't need the other constant because it doesn't really matter what the number is. So you can transfer it to either side of the equation. So then for the next part, we'd want to isolate y. In order to isolate y, we're just going to do it like a normal equation now. So the first thing we do is to add this to both sides of our equation. So that would give us 0 equals 2 natural log y plus t plus some constant. Next, you would divide both sides by 2, giving us 0 equals ln y plus t over 2 plus some constant over 2. So the next part is where this starts to get interesting. So we're going to be using the logarithmic definition of a equaling the natural log of e to the a. And this is important so that we can rewrite all of our terms in a common format and then simplify them down. So here's how it would look. So you would have something like ln t over e squared plus ln c over e squared. And since we were just using a definition, we're not changing anything in the equation, so we don't actually have to do anything to this. So we'd have plus ln y is equal to the natural log ln of e to the 0th power. Now you may notice something interesting. We can now actually combine all of these terms since they're all logarithms with the same base. So we'll get the natural logarithm of, so the natural log of their constant over e squared times our time over e squared times y. And that's all going to be equal to the natural logarithm of e to the 0th power. Now you can, once you get rid of the natural logs, it's going to look like the constant over e squared multiplied by our time over e squared y equal to e to the 0th power. So now that you're left with this, all you have to do is solve it like a normal equation. So now all you do is to divide both sides by everything here but 1. So you will do this side divided by c1 over e squared times t over e squared, and then e to the 0th power is just 1. So when you divide both sides by that, you get 1 over c1 over e squared times t over e squared, equals y. And saying this is the same thing as saying e to this to the negative power. So as your final result, you will get y equals e to the negative c1 over e squared t over e squared. And those two are multiplied by each other, and we leave them separate for a reason. But this is going to be your final answer. And the reason we leave them separate is, if you recall the original growth and decay model, this right here is actually representing your constant, and this right here is representing your time. So if you need to reference either one of those points when you're writing the rest of your problem, if it continues that far, which it will later, you can always reference these 2 points in the equation without having to solve for them. Now, when you want to look at this and see whether it's exponential growth or decay, all you have to do is look at this sign in front of your constant right here. And this is actually a negative. So this problem represents exponential decay. So that is the lesson on differential equations and growth and decay for section 8.4 in the book.